Aloha, everyone. My name is Rodrigo Romo, and I'm with PISCES, or the Pacific International Space Center for Exploration Systems in Hilo, Hawaii. We are a state-funded agency, as I mentioned, based in Hilo on the Big Island. And PISCES has been involved in previous in-situ resource utilization tests on the slopes of Mauna Kea. The three main areas of development that we have in PISCES include a robotic village, which is what I'm going to be talking to you about here today, an advanced laser communication system that we're working closely together with NASA, and a 3D additive basalt manufacturing and laser printing. Those two other projects ultimately come together and play a big role on the robotic village. Anyways, some of the previous work that has been done with PISCES used to be under the University of Hawaii Hilo, but in two years ago, we were separated and we are our own entity, as I said before, state-funded. In the past, we've been providing and facilitating the infrastructure and support, on-ground support to different space agencies to do tests on the slopes of Mauna Kea. In 2008, we did RESOLVE, the Regolith Environment, Science, and Oxygen and Lunar Volatile Extraction, which was involved with NASA Kennedy, Carnegie Mellon, and other companies, Michelin in Switzerland, which tested some lunar wheels, and other companies. I'm just going to go quickly through these tests because it's not the main objective of the presentation. However, if at the end you have any questions regarding these prior tests, I'll be glad to answer them. In 2010, we did the Dust-to-Thrust project with the Canadian agency and NASA. It included a platform called Pilot to process oxygen from iron oxides in the surface regolith. And the main purpose of this test was to be able to extract oxygen from the regolith and Mauna Kea that's trapped in as iron oxide in the soil. Basically, there was a rover that would be collecting sand soils from a selected test site, dumping into Pilot, and Pilot would do the oxygen extraction. There were two platforms tested on that occasion. The other one was Roxygen. Not a very creative name. You can break it down. It's basically a means to extract oxygen from rocks. Also at Mauna Kea, and in this case, it was a different type of loader that would dump the regolith onto the base platform, and using heat, it would extract the oxygen in form of water vapor from the rocks, collect it. It could be stored as water, or it could be split into hydrogen and oxygen, with the theory of that then being used as a rocket propellant. Both tests, by the way, were flexible. Not flexible, were successful in extracting the oxygen from the rocks. The key to what we're doing right now is we're utilizing flexible platforms based on a design made by Ontario Drive Gear. It's going to be our main rover. And the open platform, the open payload platform design of this rover allows us to mount different types of payloads on the rover to perform different types of tests and tasks at test sites in Mauna Kea. So why Hawaii? I mean, why do we want to go to Hawaii? It might as well go to Mars. It's just about as far. But anyway, the reason is it's been found that the chemical composition of the volcanic ash on the slopes of Mauna Kea and Mauna Loa are very similar to the regolith down on the Moon and on Mars. Also, the terrain on the Mauna Kea provides very good analog conditions to the Moon and Mars. It's very similar conditions, without the low gravity, of course, but geologically, it's a very similar situation as you have on the Moon or Mars. This is a picture taken by, I believe it was Curiosity, if not one of the other rovers in Mars. It's one of the pictures of the slopes of Mars. Right now, you can see this is a picture of one of our test sites in Mauna Kea. Other than the blue skies and white clouds in the background, it is pretty much the exact same terrain as you would find on Mars. And the Moon is the same situation. This is a picture of the Moon, and this insert is a picture of one of the test sites on Mauna Kea. It's basically the same conditions. There's one of our coupled rovers. This is a soil extraction rover with a hydrogen fuel cell trailer behind it. So why a robotic village? It's pretty much taken for granted that if there is going to be long-term settlement in space, the infrastructure is not going to be built by human hands. Infrastructure will be built by remote control and autonomous navigation robots that are going to get some of the prep work done prior to human arrival. Robotic technology needs to be developed, tested, and integrated with other components for vertically integrated ISRU, or in situ resource utilization. Basically, we need to send rovers or robots up there to lay out the groundwork before we can send humans. So what is vertically integrated ISRU? Basically, it includes all the steps from prospecting. You're going to have prospecting rovers searching for hot spots, finding out where water is, finding out where oxygen-rich soil is. You're going to need some other equipment to do the mining and the extraction of the resource. You will need a transportation that will carry your ore or your water, your ice, from the mining site to the next step, which will be the processing site. And the processing is where you're going to be doing your extraction, whether it's oxygen extraction, water extraction, separation. It can be then taken to storage, it can be taken for refining, or it can be taken for separation. The water you'll be collecting from the craters in the moon or Mars is not going to be very pure or very clean, so it's going to have to go through some filtration or refining process. The water you collect, if you want to split it into hydrogen and oxygen, will have to go through a separation process. And then finally, you'll have the utilization of the resources. So what will this look like? Well, this is some imagination of what a robotic village might look like. Obviously, you'll have rovers in the center. You have a rover getting off of a lander as it recently approaches or lands into Mars or the moon. You'll have down in the center, you have a prospecting rover that's going around looking for oxygen-rich soil. On the left, lower left, you have a rover delivering, as a transportation delivering the regolith into the oxygen extraction platform. Lower right, you have a solar concentrator that is taking the solar energy and concentrating it into a high-energy beam that's hot enough to melt the regolith that's being delivered to the extraction unit, and as it melts it, it releases the oxygen from the regolith. The two images on the upper right and left is what a printing rover might look like. The one on the left is shown printing launching or landing pad along with a road that will be used in the platform, the base. The one on the right is printing out what could be a shelter or a dome. Now this is I've shown this presentation before and asked people if this is fact or fiction. Well, except for the two upper images, all the other ones have been done and tested in Mauna Kea. And the one on the upper right, you might recognize that platform as Athlete. That is an existing platform that NASA has, and it can be adapted with a 3D printing arm. And that's where one of our projects is coming about on 3D printing. This is what I'm talking about. There is some work being done in Southern California with concrete 3D printing already. I believe they're able to print out a house in a period of about 48 hours. We're going to be doing some work on basalt laser printing, and that is using and we're going to be testing different technologies: laser printing, microwave, sintering, and that's going to be using the regolith that is available, in our case in Mauna Kea, on a planetary situation, the regolith that's available on the Moon or Mars, and use that as the printing media to print launching pads, landing pads, shelters. Right now we're about to do our first print test on some sidewalk slabs that will be placed out here in Hilo and compared for wear and tear against regular cement. The next step we will do after that, we will be printing a 3D printed dome that will be used as a shelter for a rover using basalt. So that all is taking place. Laser communication, we're working with NASA, and starting this summer, we're going to be doing a weather study in the slopes of Mauna Loa, not Mauna Kea, but Mauna Loa, to determine whether this will be the first Earth-based permanent laser communication relay station for NASA. Their plan is to replace radio frequency communication with laser-based communication in space and get a much broader broadband and speed rate. That's also happening this summer. Now, about the design challenges for this presentation, for this workshop, recently, thanks to high-definition cameras orbiting the Moon and Mars, lava tubes and skylights have been found in those bodies. And the great thing about lava tubes is that, well, one, bringing back the question as to why Hawaii, the Big Island is littered with lava tubes. We have lava tubes all over the place. The picture on the upper left is a picture of a skylight on a lava tube on the Moon. The one on the right is just a couple of 100 yards off of the airport in Kona on the Big Island. So we have very similar situations on the Big Island, which give us the opportunity to do testing on lava tubes. The challenge here is, how do you map a lava tube? Are you going to build a crawling rover, a rover that can rappel down to the tube? Is it going to be an aerial unmanned vehicle that goes down into the lava tube and with a system of LiDAR is going to be doing a 3D mapping of the lava tube? That's the design challenge we have right now. How do we map and characterize these lava tubes? And the importance of lava tubes is that they will provide shelter. It might be easier to build the habitat sections under the lava tube, and it will protect shelter against meteorite bombardment. It will provide a thermal regulator. The idea is that the temperature fluctuation inside a lava tube is not going to be as great as it is on the surface of the Moon or Mars. So lava tubes can be a great advance or a great aid in the development of extended habitation in space. And they provide a wonderful challenge for today. How do we explore these lava tubes? We need to develop and build the technology for rovers capable of going down into those lava tubes through the skylights and then mapping and characterizing the lava tube themselves. So with that, I'd like to just say that PISCES' goal is to make the PISCES Robotic Village in Hawaii the gateway for ISRU technology development and integration through multi-agency and multinational collaboration. We would like to see all of you come over to the Big Island and develop your technologies and test them there with us. At this point, I'd like to close my presentation. Mahalo nui loa. That means thank you very much in Hawaiian. And malama pono. Take good care. And if you have any questions at this point, I would like to address them. Thank you.